Those are my comments. Science is the most challenging of human endeavors. Scientists every day, with a lot of creativity and insight, come up with discoveries that help us improve our health, understand climate, earthquakes, and other characteristics of our planet, preserve our environment and our ecosystems, and understand the universe and the world we live in at large. For several years, I've been working with scientists in many disciplines, and my belief is that science advances very, very slowly, and I think we can help. So I'm here to convince you that we should be developing machines that actually help scientists be more productive. And my research is, I'm a computer scientist, and my research is in artificial intelligence. I'm interested in creating these machines that help scientists be more efficient. And I'm going to start by showing you two examples of why science advances very slowly, in my view. This is the first example. My friend Phil Bourne and his colleagues at UC San Diego are developing drug discovery methods. And some years ago, they published a paper that is very well known, and it documents their method to discover drugs. In this case, they discovered drugs that interact with tuberculosis. What they did is they took all the proteins of tuberculosis, they took all the drugs that are in the market, and they developed very sophisticated methods that compared pairwise drugs and proteins. And their goal was to find what drugs interfered the most with tuberculosis. And this method is very sophisticated. It uses very advanced computer programs and software to do this. We worked with them to go through the paper and try to reproduce this work and use it for other organisms that were not tuberculosis. And what happened is that we actually tried to quantify how hard it was to reproduce their method. And we measured very carefully how long it took, and it took about 3 months to reproduce the method that they used in the paper. 3 months is a very long time. It means that another scientist that wants to apply this method for something else has to invest months of time to do that. That many scientists start trying to reproduce the work that was done in other papers, and they cannot do it. They spend a lot of effort, and then they give up. So this is an example of things that take a long time to just reuse methods that are published in the literature. This is a second example. This is work by Tom Harmon and his colleagues at the University of California, Merced. They have a lot of sensors along the Merced River. And what they do is they take data from those sensors and they try to understand the effect of rainfall, snow melt, and a lot of the human interventions around the river. For example, agriculture that releases fertilizers in the water. So what they do is they take daily readings from the sensors, and they spend a lot of time preparing the data. They have a lot of methods to clean errors that come in the data from the sensors, to reformat the data and prepare it in ways that they can use to model what happens in the water. They spend many months doing this. And this means that from the time that, for example, fertilizers are released to the time that they understand their effect in the water, it's been many, many months. And they kind of learned what happened much too late. So this is another example where science is progressing very slowly, and it really has effects on how we can use the results of science efficiently. This is also not unusual. A lot of studies show that scientists spend 60 to 80% of their time just preparing data. So what I find is that most of a scientist's time is done preparing to do science, and very little time is spent actually doing science. And my goal is to try to reverse that proportion. I think that scientists need new machines, and I'm going to make an analogy with the Industrial Revolution. I think we need an Industrial Revolution in science. This, if you recognize it, is a spinning wheel. So a spinning wheel was used for centuries to take natural fibers and create yarn. It's operated by a single person. Almost every household has one of these, and people spend a lot of time just pulling yarn together. This is a different kind of machine. It's a spinning jane. What this machine did is actually allow one person to spin several yarns at the same time. And the invention of this machine really changed things. People started to think about new kinds of machines that could really change the way that people produce goods. And that led to lots of new machines. And the Industrial Revolution really changed how we manufacture goods. This is a factory floor from today. This revolution has continued. You see here a lot of robots that actually take on a lot of tasks. And I think this has fundamentally changed how we produce everything in our lives. I think that science needs an industrial revolution. It needs a revolution of this kind, and something that really helps scientists be more productive. And I think it's not just a matter of the scientists being more productive, it's also a matter of them having the tools and the ability to tackle more complex problems. On the left is an example where I'm contrasting two types of problems. On the left is an Egyptian with polio. So polio has affected humanity for millennia. And studying polio comes down to finding the organism that causes polio and then researching a vaccine and then spreading the vaccine to people. So polio is now practically eradicated. In contrast, on the right, I'm showing you cells that have a type of brain cancer. It's called glioblastoma multiforme. And this kind of cancer can kill a person in months, and we don't understand what is it that happens to those cells for that person and their organisms for that to happen. So cancer is a tremendously more complex thing to study, and I think that scientists need better tools, not just to be more efficient, but to really tackle these very complex problems. We need to help them with that. So my research is on artificial intelligence techniques that help us build intelligent research assistants for scientists. They have intelligent capabilities. They can actually make decisions and do things on behalf of the scientists, assistants, true assistants. And they also can undertake discovery tasks. They understand something about how science is done. So very central to being able to develop these intelligent research assistants is to be able to allow the machines to understand how science is done, the process of science. So this is an example of how we do it. We create workflows that capture all of those programs, all of that software that scientists run to analyze data into something that we call a workflow. It shows all the dependencies of that software and how it processes data. And I'm showing you here a workflow to create the drugome for an organism. The inputs can be any set of proteins or any set of drugs that are in the market, and it will go through the same methods that the scientists did, except that you can just reuse the workflow. So instead of spending months to try to reproduce the method in the paper, you can actually just run the workflow in minutes and apply it to new diseases. This is another example. This is a workflow that actually captures the process to understand water metabolism and what happens in the chemistry of the water. So one of the steps is to actually estimate how much oxygen, how much air mixes into the water. And there's actually different methods to do this depending on how deep the water is, which means how much it's churning. And so this workflow actually has a representation of that and is able to, depending on what the sensors read that day and how much the flow of the water is, it will pick a different method to estimate this aeration, this combination of air in the water. So these workflows are being intelligent about how to do the science and about how to analyze the data. This saves scientists time. They don't have to spend months preparing the data, but it's also allowing them to have responses on the same day about how fertilizers, rain, and snowmelt are affecting the river, so they can take immediate measures. So having these intelligent research assistants really changes the game for scientists. So for one, they don't have to re-implement methods that others have published. They can just reuse them. And instead of taking months, they can take minutes to do that. They don't have to spend months preparing data. These intelligent research assistants can run these workflows and take minutes to run them instead of months. But they also can delegate decisions and configurations and let these intelligent assistants analyze the data based on what the data is and what the data needs. These are all very good advantages because it makes the scientists more efficient. But there's a much more profound innovation here. And this is that these workflows are actually machine readable. So what this means is that the system can actually understand these workflows. The system understands what the workflows are. The system understands the process that scientists use to do science. So contrast how it works today. All the scientific knowledge is in books and papers. Machines cannot access that. However, machines can access this. They can understand what that process is and how the data analysis was done. This is a really, this really can change completely how science is done. So this is really a game changer. It enables us to develop intelligent assistants that can do very useful things for scientists. So today, the intelligent assistants that we're developing really help scientists be more efficient. They can find workflows to run. They can configure those workflows. They can create new workflows and explore new configurations of them. But there's still a lot of research that we need to do. There's still many challenges ahead for these intelligent research assistants. One is to be able to represent all kinds of processes in science. That requires representing a lot of science knowledge, and this is very complex. Once we have that knowledge, we need a lot of algorithms, a lot of techniques to reason with that knowledge and make the systems understand it and create new conclusions based on that knowledge. These assistants need to be able to explain new conclusions that they reach so that the scientists understand what the assistant is proposing. And they need to have some autonomy to make decisions about what experiments they want to run and how they want to analyze data, make some decisions in the process. They need to have collaboration skills. They need to be able to interact with the scientists and say, oh, I know you're going to do that. Let me take that on. I know how to do that. And then report the results and offer help when they can. And also ask for help when they need and say, you know, this is looking strange. I don't know what to do. Help me. So these are all great research topics for artificial intelligence in trying to understand how scientists intelligently understand data and understand the world. These intelligent assistants can take many shapes. This is an example of an intelligent science assistant that actually has sensors and effectors. So it's all embedded in the physical world. This is work from my colleague, Hod Lipson from Cornell University. So he actually has a robot in the lab, and based on what the robot is perceiving, the system has models of the world. It creates theories about what's happening in the lab, and it designs experiments to prove or disprove those theories, and then selects experiments to execute, and it's constantly running experiments in a nice virtuous circle of finding out how things work. So imagine extending the intelligence of these robot scientists and allowing them to really collaborate with scientists. So my vision is that we really need to help scientists collaborate better with these intelligent research assistants. I think that